Hello friends, welcome back my YouTube channel MS Maths. In this video, I will discuss group theory and topics of group theory that are basically cosets, definition of an example, and I'll discuss index of subgroup also, that is also a related topic, and normal sub. In the previous video that we have discussed so many topics from the basics of group theory. Okay, from the basics of group theory, properties of group theory, we have discussed different groups, and also we have discussed order of group, cyclic group, abelian group. Okay, so these all are the properties that we have already discussed in the videos are available in playlist. You can go and watch on M channel. Now, whatever the video I'm uploading that is helpful for IIT JAM, CSIR-NET and GATE. My name is Manoj Solanki, and let's start the video and let's start the topic cosets to normal subgroup. So what do you mean by cosets? First of all, you should know about what is a subgroup. If let's say G star is a group, means it is satisfying certain four properties. Okay. What are that four properties? That four properties are closure property, associative, identity, and inverse of each element. Now let's say H is any subset of G, which is also a group under the same composition. It means this is also satisfying these four properties. That is known as subgroup. So now we'll start with the subgroup only. From here, I'll see this is nothing but my subgroup of G. Okay, then I will take one element from this. This is nothing but one element. Let's say A is element of, okay, and if I will sorry, yeah, wait. So yeah, A is belonging from G. It's not like that. It may belongs from from H, but I'll take generalized case. If any element belonging from group, if I will take operation A star with H, it is nothing but whatever the element of H I'm just calling with H only. Okay, so it is nothing but A star small h, where A belongs to G and this H is belonging from H. Sorry, yeah, A belonging from G, this H is from. This set is known as coset. This particular set is known as coset. Now there are two types of. If I will operate this A in left side of A, then this is known as left coset. This is known as left coset. Okay. If I will write like this, A star, sorry, H star A is nothing but H star A, such that A belongs to G and H belongs from H. This is known as right coset. Okay. Right. There are two types of coset. First one is the left coset, another one is the right coset. Just the thing is that from where I'm operating A to H, if I will write like this, it is a left coset. If I will write like this, it is a right coset. Okay, so these are the coset. If G is abelian, now we'll talk some note point and we'll talk about some note point and results. If G is an abelian group, it means what? G is an abelian group. It means what? A star B equals to B star A. Property will holds. It means left coset of A in G is right coset. So that means simply if I will write like A star, this is what your left coset, which is simply is equals to the right coset. This is for abelian group, that is just because of this property, commutative property. Okay, now we'll take some question and we'll find the left coset and right coset of some of the. We have one example that group is Z6 under addition modulo 6 and its subset is or subgroup is 0, 2 and 4. This is a subgroup. Then find the left coset and right coset. How can we find? Just simply, these are, what are the H here? H is 0 and 4. What will be the A here? that are the element of G. Now what do you mean by G here? That is 0, 1, okay, 0, 1, 2, 3, 4 and 5. Z6 means up to 6 minus 1 to 5. Now I will take simple, it is under addition modulo 6. I'll take A is equals to 0. I will write simply A with H. Here it is also 0. Okay. And now this I'll take simply A plus addition modulo 6. Then it is nothing but what? 0 plus 0 comma 2 comma 4. It means it is nothing but 0 plus 0. Then 0 plus 2. I'm writing what? Left coset. I'm writing left coset. Okay, and it is what? 0 plus addition modulo. This is under addition modulo 6. Okay, so this is going to be 0, 2 is equal. Okay, next thing, my A is equals to 1. Then it is nothing but 1 plus addition modulo 6 is equals to what? 1 plus 2 addition modulo 6, 2, 4, sorry, 0 to 4. Now from here it is what? I will just write 1 addition modulo 6 plus 0. Okay? Then 1 addition modulo 6, 1 addition modulo 6 with 4. And this is going to be 1, 3, 1, 3 and 5. And similarly I will take A is equal then 1 plus addition 6 with H. Sorry, here it is what? Is equals to 2 addition modulo 6, 0 to 4. This is what? 2 addition modulo 6 with 0, 2 addition modulo 6 with 2, then 2 addition modulo 6 with 4. That is simply 2, 4 and this is 6 with addition modulo 6. So it is okay. So from here what can I write? What can I write? Directly I will write, so yes, next if I will take A is equal to 3, okay, A is equals to then 3 addition modulo 6 H. Simply if I will write directly then it is 3, 5 and 1 is what? Equals to 1 addition module, same as this. Okay, then if I will write A is equals to 4, then 4 addition modulo 6 H is what? Going to be here 4, 0 and 2 is again your H. Okay, then if I will write A is equals to 5, but 5 plus addition modulo 6 with H going to be 5, 1, 3. That is also going to be 1 addition. It means simply if I'll see this and A is equal to 1 all same, and here this. And now one thing, now here I have calculated left coset. What about right coset? What about right coset? What do you mean by right coset? If A is equal to 0, then right coset is H addition modulo 6. If A is equals to 1 means H addition modulo 6 is A is equals to 2, H addition modulo 6 2. Similarly, A is equals to 3 means H addition modulo 6 with 3. A is 4 means H addition modulo 4. A is 5 means H addition modulo. One thing is here. Again, these all are same. Whatever I'm marking with green, these all are same. Whatever I'm marking with blue, these all are same. And one more thing here, Z6 is an abelian group under addition. If it is an abelian group under addition, it means whatever I'm writing A addition modulo 6 equals to H addition modulo 6 with, means from here I can see left coset is equals to right coset. That's the simple case of abelian group. Okay, and now note point. Coset need not be a subgroup because first thing, for subgroup it should be a group. Let's say I can take this A addition modulo. Okay, from here this is what the coset. I can take this one. This is what coset. 5 plus addition modulo H is nothing but 5, 1 and what is the additive identity? 0 does not belongs to 5 addition modulo. Means it is not satisfying the property of group, not satisfying the property of subgroup. So that's why not like that. Coset need not be a subgroup. Now simply what about this? If I will write this 4 addition modulo 6, 0 belongs to this. Yes, 0 belongs to 4 addition modulo 6. Okay, associative property, yes, associative property hold. Okay, then identity is there, yes. Closure property, yes. Inverse of 4 is 2 and inverse of 2 is 4 is the Z6. Okay, something like this. If all the 4 properties are there, may subgroup, but it is not like that. It is always a subgroup. Okay? Need not be subgroup, not always. Simply I can give you the example that 0 plus H and 1 plus H are two different, okay, different coset, and if I will take two different coset and its union, if I will take two different coset and I'll take the union, means it can give me the whole group just using union, or its intersection is, it means these both are disjoint. From here I can simply say 0 plus H and 1 plus H are disjoint. Okay, means its intersection is going to be an empty set. But here it is what? Equals to whole group. Next, if AH and BH are two different coset, okay, sometime I'm writing in multiply, sometime I'm writing in addition, that is just because of the binary operation. Okay, AH is not like that it is in multiplication, it's depending on the binary operation. Okay, so the proper way of writing like this, A star H and B star H are two different coset of H in G, then AH intersection BH or AH is, if these both are two different coset, then either they are different for each and everything or they are equal. Just see, just two cases are there. Either they are just equal, just see all greens are equal or reds are equal. Or what about green and red? Nothing is common inside. Where is it? Yes, 0. Yes, here it is. You can see this one and this one, right? This one and this one, nothing is common. Either they both are, if these both are the different coset, then either they both are disjoint or they are completely equal. It's not like that some elements will be in that intersection. No, none of the element in that. Okay, now next question. If G is a group and H is 3Z, of course, if M is any positive integer, then if Z is what? Group of, this is an infinite group of integers. Okay, group of integers under addition, then MZ is always a subgroup that we have already discussed. If it is a subgroup, then find all the subset. First of all, we should have an idea about how Z will look like. This Z will nothing but 0 plus minus 1 plus minus 2 plus minus 3 2 plus minus infinity. What about 3Z? It is nothing but the multiple of 3. 0 plus minus 3 plus minus 6 plus minus 9 up to plus minus infinity. Okay, so from here what are the possible A? What are the possible A? A can be 0, A can be 1, can be minus, okay, 2, minus, something like this. Okay, from here if and all are belonging from where? All are belonging from this particular. So I'll take simply 0 plus h means 3z. That is what? 0 plus minus 3 plus minus 6 plus minus 1 plus 3z. Now what about this? Simply 1 plus minus 2. Okay, I'm also taking that addition also. So from here, not plus minus 2 is simply minus 2, then 4, 7, minus 5. I will take 2 plus 3z, then this set looks like 2, minus 1, 5, minus 4, 8. If I will write like this, 3 plus 3z, then it will look like 3, 6, 0, 9, and minus 3. Now you can see either they are completely disjoint or they are equal. From here I can find now 0 plus 3z, 1 plus 3z, and plus 3z are distinct coset of 3z. It means, and in where? In z. Means I will take 0 plus 3z union 1 plus 3z union 2 plus 3z give you the complete integer. You can see this thing, this and this. From here you can see now it is also repeating. This is nothing but my 0 plus 3z. Now it will repeat. From here you can see all three multiples are there. You can see all other than elements, like all non multiple of 3 elements are there. If it is 1, then minus 1 is here. If it is minus 2, then plus 2 is here. If it is 4, then minus 4. If it is minus 5, then 5 is here. Here it is 8, then minus 8 is of course there. It is 7, then minus 7 is of course. So you can get this. But on the other hand, same property, if I will take the intersection of all these distinct cosets, if I will take all intersection of all these distinct cosets, that nothing will be in the, it means 3z has only 3 different. Now the question arises, how many distinct, or you can say different cosets of 3z that are 3 distinct or different cosets. Okay, this concept arises one, this particular statement arises one concept known as index of, that we'll discuss in this. Next, let G be a group of order 10 then which is generated by A, means cyclic group. H is subgroup of G which is generated by H square, cyclic subgroup. Then find the of H. Very simple. Group G, what is the generator of this group? A. How it will look like? A square, A cube. Okay, then A power 10, because group's order is equals to power 10 is going to, because identity must. What, how H will look like? Okay, this is all about G. How H will look like? Generated by A square, means A square, A power 4, A power 6, A power 8, A power 10, which is now here. From what is H? H and what is A? From here, if A is equal to A, then A plus simply A. This is under multiplication. Yeah, it is under multiplication. Then H into A, and it is what? A cube, A 5, A power 7, A power 9, A power 11 means A power 1. Okay, this is nothing but AH, which is equals to A cube H also, which is equals to A power 5H also, A power 7H, and A power 9H. Now what about A square? G, I will take A square, nothing but A power 4, A power 6, a power 8, a power 10 means identity, a square, which is also equals to, okay, which is nothing but a square h, a power 4h, a power 6h, a power 8h, and simply is equal to a power 10h means identity in, okay, not equals to. This was the, yeah, this is the result. From here, all are how many distinct cosets? What's the index that we will see later. What do we mean by index that? Now the question arises next. Next we'll see for dihedral group that we have Z is D4. Okay, and the subset is R0 and R180. Find all coset A and D4. First of all, how D4 will look like? D4 is nothing but what? R0, R90, R180, R2, horizontal, vertical, diagonal, and diagonal. Okay, so now from here, given K is what? R0. This is also the center of group that I have already center of D4. Okay, R0 and R180 means these are the element which commuting with each element. From here, R0 belonging, I will take with D4, simply R0 into K, which is going to be R0, that is R0. Now next R180 into about this, then R180. Okay, R180 with 90, that is R180 with R180, that is going to be R0. Next take R90 into K. Okay, R90 into R0, that is going to be R90, and R90 with R180, that is going to be R2. Here it is R2. Then R270 with K, that is going to be first R270, and R270 with R180 is going to be R90. And these both are equal. These both are equal. Now I'll take H into K. Okay. Now I'll take H into, that is simply H into vertical. Okay. H into R0 is H. H into R180 horizontal. It will flip. Okay, horizontal 180. What's the 180 rotation? This was the horizontal 180 rotation. Okay, so this is the basic concept. If I will write vertical K, going to be vertical and horizontal. If I will write diagonal with K, is what? Diagonal and anti-diagonal. If it is diagonal, 180 means diagonal, 180 means it anti-diagonal. Okay, then if it is this diagonal, these are the, now how many distinct cosets want to, I am interested in only distinct cosets. How many distinct cosets are there? Just see, these both are equal. So one distinct coset is two distinct second. This one is third, and this one is, so four distinct there. What are that? See, I can write R0, R180, then R90, R270, and next horizontal and vertical, then diagonal and these are the distinct codes. Simply, if you will, so from here I will take, let's say this is my C1, is C2, C3, and this is C4. I will not D, C4. What about C1 union C2 union C3 union C4? Nothing but D4. And C1 intersection C3 intersection thing but 5 non-empty. Yeah, next we have some more results are there. Now H is a subgroup, then find HA. Then find HA is equal. From here it is saying that if you are taking A, now see from here what is the definition? A we are taking from group and H we are taking from H, and we are multiplying this together. Then we are getting Coset. If I will take A from H and I will take H from H, this is going to be equal H only. Going to be equal. Now I will say how. Simply can write what do you mean by Z? That is going to be 0. What do you mean by 5Z here? Multiple of 5. Plus minus 5 and 15. From here, I'll take element from this. Let's say 5. Addition modulo, not. Yeah, 5 addition with 5Z. What is this? 0. I'll take, okay, here it is what? 0. 5 plus 5 is 10. 5 minus 5 is 0. 5 plus, sorry, 5 plus 5, yeah. Now 5 plus 10 is 15. 5 minus 10 minus means this is nothing but it 0 plus minus 5 plus minus 10 plus equals to if that nothing but your h. Okay, this is the property. Now can one more example. D4 is there. Next, if D4 is there, then I will take R0. Okay, if I'll take R0 into K, nothing but R0, R180, H and V, same. If I will take R180 into, that is what? R1, R0, vertical and horizontal, same thing. If I will take horizontal into, means what? Horizontal, nothing but horizontal, vertical, R, 0. Yeah, this is R0 and R1. Okay, if I will take vertical into, that's simple. Vertical, horizontal, R180. See, all are my K. This is also K. This K. Okay. Now next come to the quaternion group. We'll find all the cosets of quaternion group here. Now see. Next, find all cosets of quaternion group where K is. What about quaternion group? Nothing but plus minus 1 minus I plus minus K. Where I square, J square, K square. But and also that I that I K I into J is nothing but K J into I. Simple property. My task is what? My task is here to, if I will take with 1 plus 1 into K, write 1 into nothing but what? Plus minus 1 plus minus. Then minus 1, nothing but minus plus 1. Then iota into, this is also you can see, because I'm taking A, because A is also belonging from this. A equals to, then it is what? Plus minus, then minus plus 1. Also we are writing minus of minus plus I. Now if I'll take J into K, this K is I will write H is the element of, so here I will, now what about J into H? J into H plus minus J. What about I into J is K, but J into I minus, then plus minus. Now it is not equal to, because J is not belonging this manner in all quaternion group. Next come to the S3. How can we find the cosets of S3, where subset is given like this? Okay, subset is given like this. H is identity 1 and in all. How can we find? Simply what is S3? 3 is identity 1 2 1 3 1 2 3 and 1 3. Take the element, simply identity with H is again going, because identity is also belonging from equals to, then 1 with H, that is nothing but 1 2 and 1 2 1 2, of course identity, because this will. Now here it is what 1 3 with H, with identity it is going to be 1 3. What about 1 3? I am finding the left coset anytime. All the cosets means right coset. Now right coset and left coset are not equal. Not like that every time they are equal. They are equal in only if it is in a abelian, then they are equal. Okay, what do you mean by this? Just multiplication. What is the meaning of this? 1 2 3, then 1 goes to 3, 2 goes to 2, 3 goes to 1. Here it is what 1 2 3. Now you know that this is not equals to 3. Okay, this is not commutating. Okay, 1 goes to 2, 2 goes to 1, 3 goes to 3. How will you multiply that? I explained in the permutation group. Just write 1 2 3. 3 goes to 3 here. Start from back. 3 goes to 3, 3 goes to 1, then 3 goes to 1. Then 2 goes to 1, 1 goes to 3, then 2 goes to 3. 1 goes to 2, 2 goes to 2, and it goes. From here 1 goes to 2, goes to 3. Means it is nothing but 1 2 3. Okay, so this is what the simplest case of multiplication. Now what about 1 2 3 into H? That is what with identity it is 1 2 3. What about the multiplication with? It's simply take multiplication of 1 2 3 with 1 2. From here you will get 1 2 3. This is, sorry, 1 and 3. Get and 1. So this is how you can find all the subgroups of whatever the given. Okay, so this is all about the next. Next we'll see some note point. Okay, you can find for each and every element. I am giving you just example. Now if H is a subgroup of group of of E, then H into H is again going to be H into H into H n times this is going to be. Okay, H into H, this is going to be. From here simply this is the example. Okay, so from here if I will write, from here I'll take example. What is that example? What is that example? Simply one more thing. Yes, I can take example of 2Z is group of Z. If I will take 2Z plus, it is going to be 2Z only. Okay, that's the thing. We are adding n times, then only it is on, then only of course the same thing is equals to. Okay, and one thing, Z into G into G. also 0. You are writing if the group. Okay, you are writing n times. Next, second example. This is the one first. If H is belonging from where? If let's say H is equals to center of D4 is a subgroup. The center is always group of. Then only if you'll add H plus S, whatever you are writing here, also equal. Next, if it is MZ and NZ means 3Z plus 2, then it is equals to GCD of this equals to Z only. How is equals to GCD of M? Because, yeah, not GCD, LCM of M. What's the LCM? That's 6. LCM of M equals to it. LCM is also there, but Z. Oh yeah, if I will take intersection of this 3Z plus 3Z and 2Z, if I will take intersection, okay, these two are subs. If I will take intersection where M and N both are greater than equals, both are greater than of Z, then this is nothing but LCM of M. But this is the correct reason. If I will take intersection, then it is, yeah, okay, then is correct. You can prove this theorem like this. See, what is the proof? If I will write mx plus ny, where x is belonging from z and y is from z. This is nothing but GCD of m and n. Okay, GCD of m where z. Okay, GCD of m into simply z. We'll write GCD then where z is belonging from here. I can write GCD of n of n. This is nothing k of z k. Okay, so this is all about. Now my concept arises that index of, this is very, what do you mean by index of? So number of distinct cosines, whatever I explain, number of distinct cosines, nothing but index of any subgroup, or it can be defined using the order of group divided by the, let's say I have Z6 and I have one H that is 0. There are 3 different subsets. It means order of 6 divided by order H going to order of G. Order of G divided by order of H, that is going to be 6 divided by 3. 6 divided by 3. Two distinct subgroups that we have also taken. Okay. Take example. Example G is equals to Z of 10. Okay, and H is only 5, which is generated using 5. Means from here, what is the order can be also denoted like, and also this Z10, order of Z10, and order, this is the generator. What is the order of 5? Going to be 10 here. Order of 5 is going to be 10 divided by 2, 5 subs, 5 index is there. Second example, my G is quaternion group, then H is equal to 1 and minus 1. What is the index? QA. What is the index of, what is the order? 8, that is 4 is there. 4 distinct indexes. Okay, the concept. Now next, coming to the normal subgroup. Normal subgroup is nothing but, so this is the definition. It's X is belonging from this and H is belonging from this. If you are writing this, means H X and H X inverse, because if X is belonging from G, then of course X inverse is also belonging from G. If you will write like this, then this should be inside H, and it is known as, simply it is, what is this? It is nothing but, if I will write this, left coset is of every abelian subgroup is group has normal subgroup. Because of that, every abelian subgroup has what left coset and right coset equal. That means they are from here. Simply if I write like, okay, so in any subgroup, any group, every left coset or right coset equal, then is normal. If and only if that group is subgroup is normal. And if G is normal, then all subgroup of G are, let's say, whatever Z6, it is abelian group because it is abelian as well as cyclic. What are the subgroups of this? Z1 is the sub, Z2, Z3 is the Z6. All are normal. These are what normal sub. Okay, next. You can take so many examples here. Okay. Can take G. I will take Z, or I will. These all are abelian group. Means following the commutative property. Means all sub all G here also. Now next, what about G, that is Z2 cross Z4? This is also abelian. It is not cyclic actually. Why it is not cyclic? Because GCD of 4 and 2 is not equals to 1. If the GCD of M and N is equal, then it is only the cyclic. Now it is abelian. If it is abelian, then all are all sub are normal. Okay, from here we can take example also. How many normal subgroups are there? How many normal subgroups are there? How many number of subgroups? If it is a cyclic, all subgroups are abelian. 20. Simply it is what? 20. 2 into 10. What? 4 into 10. So square into 5 is tau. What is the value of tau? 1 plus, that is going to be 3 into 2. 6 number of normal subgroups, because all the subgroups are 6 number of subgroups are there, and all the subgroups. This is a cyclic and abelian group. That's 6 number. Now there are some note points that we will see here. If a G is cyclic, then all subgroups are cyclic, that we have. But converse need not. Be. Means just see. It is what? Z2 cross Z4. It is abelian, but it is not cyclic. All subgroup are abelian. All subgroup are normal subgroup, but this is not cyclic. Is the counter example. If H is identity and G is, these both are normal because these both are, you can, trivial subgroup. These both are always normal. Center of G is always normal because center, we know that center is an abelian. Okay, center is an abelian. If it is abelian, then it is a normal. Subgroup of every subgroup of CUET is normal. They all are cyclic. And 3 are the proper subgroup, but all are cyclic. Now every subgroup with index 2, this is very important. With index 2, then all are normal subgroup. Okay, Q plus is only subgroup of Q plus, which is finite index, means it has no subgroup of finite index. Okay, this is the result. The group C by 0 has no proper subgroup in finite index, and Z plus has infinite proper subgroup. All are related to the normal subgroup. Hope I covered complete normal subgroup, cosets, and thing which is. So if you are understanding the concept, enjoying the video, getting the concept, please like the video, share the video, please subscribe the channel. Keep supporting. Thank you. Bye bye. We'll meet in one next. Thanks for watching my video. Thank you. Bye bye.